Hello, my name is Shiyang Liu. My course is MSc Robotics. My presentation is about the modeling of geometric and kinematic variations in landing gear assembly. My supervisor is Professor Ashutosh Tiwari. First, I'll give you an introduction about the topic which I'll present here, which is tolerance analysis. Some literature and theories will be given. Then I'll move to model and simulation. Finally, I'll talk about the results of the simulation and give the conclusion. So my project is related to Airbus Future Landing Gear project. When the landing gear is retracted, the gaps and steps between the landing gear door and the windscreen must be within acceptable limits. Currently, a lot of manual adjustments are required. To increase efficiency, this project aims to model and simulate the landing gear system installation variations. Here are the project objectives. The history of tolerance design can date back to the inception of mass production. The aim of tolerance analysis is to study the dimensional and geometric variations of the assembly due to a stack of dimensions and tolerances that are applied to the assembly's components. A modest investment during tolerance assignment can yield substantial benefits in the form of reduction in manufacturing costs. A systematic approach for tolerance design can estimate the accumulation of individual tolerances on the assembly dimension. However, there are some different tolerance-related problems in different stages of life cycle. So there are different models for different problems. Here I will only talk about unified Jacobian-Torsor model. The Jacobian model is suitable for tolerance representation, and the Torsor model is suitable for tolerance propagation. So the unified Jacobian-Torsor model combines both of their advantages. The Jacobian model is a kinematic-based method which uses transformation matrices for open chains in robotics. The Torsor model describes the small displacement variation of features with constrained torsors, which define the extreme limits in the 3D tolerance zone. Here is a simple comparison between the unified Jacobian-Torsor model and the other common models for tolerance analysis. Recently, Jacobian-Torsor model have been more used in tolerance analysis. For example, landing gear kinematic accuracy analysis and piston engine tolerance analysis. However, there is no combination of kinematic tolerance analysis, tolerance contribution analysis, and cost optimization. In my project, these aspects will be all discussed. As I mentioned before, the Jacobian model is a kinematic-based method which uses transformation matrices. The Jacobian model expresses the effect of functional elements, which is Fe, on functional requirements, which is Fr, in the tolerance chain. An Fe can be a point, a line, or a surface of the part. Two Fe's separately belong to different parts, constituting an contact Fe, while two Fe's coming from one part make up an internal Fe. It is a matrix whose columns are extracted from the various homogeneous transform matrices relating to the reference frames of the Fe's to that of the Fr. It can be formulated as this. Here, matrix R0I is the local orientation change of frame I with respect to original frame 0. Matrix RPT is a projection matrix designating the unit vectors along local axes respectively for tolerance zone tilted according to the direction of tolerance analysis. Matrix WNI is a screw symmetric matrix allowing the representation of the vector among the ith and nth frame. Matrix R times W reflects the leverage effect when the small rotations of Fe are being multiplied by terms of the Jacobian matrix. The Torsor model is a small displacement screw used to represent the position and orientation of an ideal surface. Here the figure shows small displacement torsor of a surface. In the torsor matrix, Alpha, beta, and gamma indicate the rotational vectors around the axes x, y, and z in the local reference system respectively, and U, V, W are three specific translational vectors along the axes x, y, and z respectively. The unified Jacobian-Torsor model is an innovative tolerance analysis method which uses the Jacobian matrix for tolerance propagation and uses the small displacement torsor for tolerance representation. Its construction combines the advantage of both two methods. The relationship between Fs and Fr is shown. Fr means functional requirement represented by the translational and rotational vector, and it's the result. J means Jacobian matrix. Fe means torsor model for functional elements. Due to confidential problem, the landing gear model I used in the project is developed by MATLAB team, and it can be simulated in Simulink. Here the image shows the extended and retracted landing gear. As you can see, the left part is the main landing gear and the right part is the landing gear lock system. The main landing gear is controlled by a hydraulic cylinder, and in the middle of the main landing gear is where the landing gear fairing is installed. To simplify the model, only the main landing gear and the hydraulic cylinder is considered in the model. Figure 4 shows the simplified landing gear model. Here, an assumption is made to simplify the calculation, that is, when the landing gear is retracted, the angle AEH is 90 degrees. The actual situation may differ from this. ABE is the base of the landing gear, and all other parts are installed based on ABE. CD is the hydraulic cylinder. HI is the landing gear wheel and the lock position. JK is the landing gear fairing installation position. C and D are two joints. RC and RD means the joint clearance. Part 1 to 8 is where the tolerance exists. The geometric dimension is estimated from the model provided by MATLAB. It is not so precise, but it's still acceptable. The tolerance for each part is determined by the ISO standard, ISO 286-1. Here is the IT grade table. In this project, IT grade 2 is chosen. The simulation is implemented by Monte Carlo simulation in MATLAB, and the tolerance distribution is normal distribution. Here is an example that how Jacobian-Torsor model is built. Refer to the method introduced before. A Jacobian matrix and a torsor matrix can be built. Here I means length and D means tolerance. Build the matrix for 8 parts and multiply them together. The result for Fr can be obtained. The simulation is done for 10,000 times. Each time the deviation for part 1 to 8 is randomly chosen in normal distribution, and all of the results are stored. Here is the visualization for the landing gear fairing. Blue frame means the nominal position, and red frame means the simulated position. Clearly, there will be gaps and steps between the ideal surface and real surface. The gap and step can also be calculated by Figure 5. Figure 6 shows the deviation distribution of the landing gear. Since the tolerance is in normal distribution, so the deviation is also in normal distribution. The result of landing gear fairing is the same. Figure 7 shows the landing gear fairing tolerance contribution of the different parts. The bar chart shows the tolerance contribution for part 1 to 8, and the red line shows the accumulated tolerance contribution from part 1. According to the figure, part 3, 5, and 8 contribute most of the deviation. Part 1, 2, 4, 6, and 7 contributes the least of deviation. To have a deeper exploration of the result, a control experiment is implemented. Figure 8 also shows the tolerance contribution. The blue bar means IT grade 2 for all the parts. The red bar means IT grade 18 for part 2 and 6, which is the maximum IT grade. The orange bar means IT grade for all the parts. The figure shows that higher IT grade will bring more deviation. However, considering the cost optimization, higher IT grade for some parts, such as Part 2 and 6, will not bring much more deviation to the system. So we can have an idea that for the parts which contribute less deviation, the requirement for tolerance can be very loose to reduce costs. As for model validation, the deviation distribution is the same as the tolerance distribution, so the model is correctly implemented. The left matrix shows the result from Jacobian-Torsor method. The right matrix shows the result by deterministic tolerancing method, that only the translational tolerance is considered. The Jacobian-Torsor method can not only give translational deviation, but can also give rotational deviation. The deviation may be higher, that is because the joint can amplify the deviation, which is called leverage effect. The result will be more accurate. To sum up, the tolerance can be obtained through the analysis of the combination of Jacobian-Torsor model and Monte Carlo simulation. The effects from joint clearances can be easily estimated by this method. The contribution of the variation from different parts can be obtained to help for system optimization. Some parts can have loose tolerance requirements for lower cost, and joint may bring more variation into the system. Let's move to the future work. First, kinematic movement error can be obtained by changing the angle. Also, the tolerance distribution can be selected differently. Second, IT grade for each part can be customized for trade-off between cost and tolerance. Thank you very much for listening.